Welcome to section 7.5, broadcasting live from the Arctic regions of my basement bunker. This is Jeff Parent. We're going to work on an overall integration strategy. We've learned a lot of techniques of integration, so let's summarize a few of them before we get busy on working with some of them. So the first thing you want to do, if possible, is simplify your integrand. It could be distributing, like we did in the first line up here, or playing around with your trigonometric functions, redefining things that way, squaring things out. And one more that I'll point out that they didn't really show here is that you can use an identity. For instance, 2 sine x cosine x is really a sine of 2x. So those two things are interchangeable. And we'll actually use that identity later today. Now, if certain simplifications like that don't work, then try and look for an obvious substitution, something like this. If you have part of your integral with 1 power of x and part with the next lower power, like this one, going from a 2 down to a 1, that's a natural choice for a U substitution, because when you differentiate, you always lower the power of x. Now, there's some less obvious U substitutions, and I think we'll use one as well today. Less obvious one would be U equals ln of x. And the thing that's neat about that is that as part of your du, look where this x term ends up. It ends up in the denominator. And there's a similar thing that can happen when you're working with U equals the square root of x. Of course, you can rewrite that as x to the 1/2. When you differentiate it, oops, I left out the 1 over 2. Shame on me. 1 over 2. There we go. And then 1 over 2 again. But look what happened to the derivative there. That U term that we defined ended up with a square root of x in the denominator. So again, it's kind of an interesting thing that'll happen, and it can be useful in certain substitutions. If the low-hanging fruit, the easy things don't work, then try thinking about some other things. If it's a product of powers of sine and cosine or tangent and secant, then the techniques we learned in section 7.2 will work out. Remember, what you want to keep in mind is try and find what you're going to use for your du substitution, and then work backwards to figure out what u has to be, and then work from there. Rational functions, that should be pretty easy. If you see a rational polynomial, first thing first, you want to divide the numerator by the denominator if the degree in the numerator is greater than or equal to the degree in the denominator. Integration by parts. This one, this is something you kind of get forced into. It's like, all right, well, nothing else seems to be working. I'll try this. Not quite so much with radicals of a certain form. So we had some substitutions from section 7.3. If a radical occurs in, say, this kind of form, then maybe some of these substitutions from section 7.3 will work. I think I sent those to you in a handout. So that's these substitutions here. One other thing to keep in mind is the integrals that lead to your inverse trig functions. We'll be using a couple of these first two today. So you might want to make note of those. We'll go back to those in a little bit. But for starters, let's work with this one. And this one right off the bat seems like, well, wait a minute, I don't know. I mean, it doesn't look like a U substitution because you've got two obvious choices for U. Square root of y, well, that's not going to lead to anything because it's not going to cancel out my ln of y. And ln of y, when I differentiate that, nothing's going on there either. It's not a trigonometric type integral. It's not a rational polynomial. So, well, you're kind of getting pigeonholed into a integration by parts. So let's do that. And what catches my eye here is that that natural log term, when I differentiate it, gives me 1 over y. And that gives me hope because I'll probably be able to do something if I can get rid of that natural log. So let's try u equals ln of y. dv has to be everything else, so square root of y dy. Let me write that as y to the 1/2 dy. du equals 1 over y dy. Okay. v here, when I integrate that, I'm going to have u to the 3/2, so add 1 to the exponent, divide by the same exponent. Of course, the shortcut on that is multiply by the reciprocal of that exponent, so that'll be 2/3. Just double check it. 3/2 times 2/3 gives me 1. Subtract 1 from the exponent, boom, looks good. So let's put that together. It's going to be u times v minus the integral of v du. So let's rewrite that. U times v. I'll put the v part out in front. 2/3. That'll be y to the 3/2 times the ln of y. Y to the 3/2 ln of y minus the integral of v du. So that's product of these two. And this is what I thought would happen, is that that y here and this y here, when you multiply them together, we're going to get some cancellation. We'll just end up with a nice function of y, a nice polynomial term. So 2/3 y to the 3/2 times 1 over y dy. And this term here is going to cancel. So think of that as y to the negative first, add exponents, you're subtracting 1 from that. Okay, so that's going to be 2/3 y to the 3/2 ln of y minus the integral of 2/3 y to the 1/2 dy. And let's integrate that. 2/3 y to the 3/2 ln of y minus 2/3 times, well, when I integrate this, it's just like integrating this up here again. So I'm going to end up with 2/3 y to the 3/2 plus a constant. And then I can combine these a little bit, maybe pretty this up. If you really wanted to, you could factor out a greatest common factor of y to the 3/2 or 2/3 y to the 3/2. So let's just write it simply first. Like this, minus 4/9 y to the 3/2. This is probably what I would expect on an exam, something like this. If instead you got a little fancy, so you know what, that term and that term are the same, I'd like that. I'd be happy to see that. That'd be 2/3 y to the 3/2. And that would leave behind ln of y minus 2/3 ln of y minus 2/3 plus a constant. So kind of a nice friendly one to start with. Ooh, but wait, there's more. I guess I overlooked the fact that this was a definite integral. So if it's a definite integral, let's go back here. So the integral from 1 to 9 of the square root of y ln of y dy turned into this. Now I don't need the constant if I'm working with a definite integral. So this is just going to be 2/3 y to the 3/2 times the ln of y minus 2/3 evaluated between 1 and 9. And let's see what happens when we put in those. So let's see. So for the first one, it's going to be 2/3 of 9 to the 3/2 times ln of 9 minus 2/3. So that's our upper limit minus the lower limit. And at least in the lower limit, we'll get a little bit of a break. We're going to be putting in a 1 here. So this is going to be 2/3 ln of 1 minus 2/3. And the nice thing for us here is that ln of 1 is 0. So let's get rid of that. That's 0. So I'll end up with minus 2/3 times minus 2/3. It'll be a plus 4/9 there. Let's see what happens with our first term. That'll be 2/3 of 9 to the 3/2. So it's like the square root of 9 and then cubed. So it'll be 27. 27 times 2/3 would be 18 times the ln of 9 minus 2/3. And we said we had plus 4/9 here. Yeah. There we go. Now, I'm sure if you want to distribute this, we could clean that up even further, but you get the idea. That'd be minus 12 plus 4/9. Close enough. Let's keep going. Let's try some more here. Are there any questions on this one? Something that you're not sure about? So again, we kind of got forced into a integration by parts because it didn't seem to fit the pattern for anything else. So now, if something does fit the pattern of something else, let's go for it. But this one didn't. So how about another one? Well, just a quick FYI, the problems that I chose here are reflective of the homework that you have to do, and that's going to reflect the test that I give you. Now that one looks pretty familiar. In fact, it's close to something that we've seen just a little bit ago. I showed you this one right here, the arctangent. I'll have a constant squared plus a u squared, and that turns into 1/a times the inverse tangent of u/a. So I gotta see if I can't make it look like that. The problem that I'm facing though is that I've got a t to the 4th. So let's play around with this a little bit. That's t dt up here. What if I wrote that as t squared squared again plus 2? That's interesting. That's t to the 4th. It seems like an innocent little change. But what that allows me to do, if you start taking a look at t squared and t, that has a nice relationship. This exponent is 1 less than this one, and that's suggesting a U substitution. And looking at what I have in the integral, I've got t dt, so I'll multiply both sides by 1/2 and get 1/2 du equals t dt. That way I can make a nice 1-to-1 trade. This goes in for this in the integral, and in the bottom we'll have a u squared. So let's take a look at that. That's going to be the integral of 1/2 du over u squared plus 2. And that's looking an awful lot like my inverse tangent. In fact, let's look back at our inverse tangent a little bit, see if we can't make it look like the inverse tangent even more. So with the inverse tangent, I want an a squared plus a u squared, and that turns into 1/a plus the inverse tangent of u/a. That's pretty close to what I've got. So let me clean this up a little bit. I'll do that by taking the 1/2 out in front, and then I'll switch this around. I'll put the u squared here, but I need to write this as something squared, and I can do that as the square root of 2 squared. That's what I needed. This is in the right form. So if you want to take a quick look back, I need 1 over a, so that's going to be 1 over the square root of 2 times the inverse tangent of u over a, so u over the square root of 2. And because this is an indefinite integral, we'll put in a constant like that. 2 to the first times 2 to the 1/2. Well, we can rewrite that as 2 to the 3/2 inverse tangent. U is taking the place of t squared over the square root of 2 plus a constant. Beautiful. Okay, let's keep rolling. So the next one we'll give it a shot at will be this one. And let's do the integral of 25x squared dx, square root of 25 minus x squared. Now the bottom part looks pretty familiar. It looks a lot like my inverse sine. It's not quite my inverse sine because I got some stuff up on top. And it's not just, you can't really easily get rid of that x squared term there. So, well, you do have a square root here. And it does look a lot like that substitution that I gave you for our first test right up here. It's certainly not a partial fraction. It doesn't lend itself to a U substitution very easily. So let's give this one a shot. And in particular, x is going to be, well, a times sine of theta. In our case, a is going to be the square root of 25 or just 5. So let's do that. X equals 5 sine of theta. And let's see, dx is going to be 5 cosine of theta d theta. And I'll tell you what, let's put in some limits here, 0 to 1/2. Now this is a little bit different than your typical U substitution. Usually we substitute in U equals some function of x, but here we got x equals some function of theta. So yeah, that's kind of a pain. Hate when that happens. So if we're going to make that substitution, then we got to change our limits of integration. Ah, boy. So these limits are for x equal 1/2. So this is kind of unfortunate here that we have limits, but it's what we got to deal with. So let's keep in mind that x is going to be 0 or x is going to be 1/2. So we need to put that in here. Now the lower limit is going to be okay. I think we're okay with that. 0 equals 5 times sine of theta. So divide both sides by 5. 0 equals sine of theta. And the easiest solution for that is that 0 equals theta. Okay, so we're good on that one. What about the other one? Well, the other one's a little bit more work. 1/2 equals 5 sine of theta. If you multiply both sides by 1/5, 1/5 times this, 1/5 times this, the 1/5 cancel that, leaves me with 1/10 on the left-hand side equals sine of theta. And then to solve, we need to take the inverse sine. Inverse sine of 1/10. That's going to be my new value for theta. So kind of a really ugly limit here to keep around the arcsine of 1/10, but it is what it is. That's what we got to work with. Okay, let's finish off our substitution then. So that's going to be the integral from 0 to the inverse sine of 1/10 of 25 times 5 sine theta squared over the square root of 25 minus 5 sine of theta, again squared, and then dx gets replaced by 5 cosine of theta d theta. So let me put that here, 5 cosine of theta d theta. So a lot of things to simplify here. Let's see if we can't do that. We'll start with our integral again, and its limits, 0 to the arcsine of 1/10. 5 squared is 25, times 25 is going to be 625, times sine squared of theta. In the denominator, this is going to factor. It's going to leave me with 25 minus 25 times sine squared of theta. If I factor out the sine of theta, or excuse me, I factor out the 25 times 1 minus sine squared of theta, I hope that you recognize that what I'll end up with is 25 times cosine squared of theta. 25 cosine squared of theta. And over here, I still have my 5 cosine of theta d theta term. Now there's some good news here. Square root of that is 5. Square root of this is cosine of theta. So we get a nice big cancellation here of this and that. All that disappears, leaving me with the d theta and the 625. So I'll take the 625 out in front, 0 to sine inverse of 1/10 of 625 times sine squared of theta d theta. All right, this one we can work with. Let's do that. That's going to be 625 times the integral from 0 to sine inverse of 1/10 of 1 plus, that should be a minus there, right? 1 minus cosine of 2 theta. All over 2. And then our d theta term. And let's continue. I'll take the 2 out and integrate that. So 625 or 2. And integral from 0 to sine inverse of 1/10 of 1 minus cosine of 2 theta d theta. Okay, now we can find some antiderivatives. These are things that we can deal with. So that's going to be 625 over 2 times 0 to arcsine of 1/10 of theta minus, well, let's see, if I was differentiating, I'd end up multiplying by 2, but since I'm integrating, I have to divide by 2. So it's going to be sine of 2 theta over 2. Now, my habit in doing these problems is I usually draw a triangle as soon as I see that U substitution. I didn't in this particular one, but it's not too late. Remember our substitution was way back at the beginning. We had x equal 5 sine of theta. That means x over 5 equals sine of theta. And I can draw a triangle that matches that. And it's going to look like this. Of course, all my triangles, when I draw this, kind of look like this. I always draw a first quadrant angle. Sine is opposite over hypotenuse. I'm sure that most of you are probably thinking of SOHCAHTOA about now. That's good. So opposite is x. This is 5. If I solve from the Pythagorean theorem for this side, call it a squared plus x squared equals 5 squared, or a squared equals 25 minus x squared, or a equals the square root of that. 25 minus x squared. Now it's reassuring to see this here as part of your triangle because that radical term was part of your initial integrand. If that doesn't happen, if you don't see this radical appearing in your triangle, then there's a mistake someplace. It should. Okay. It's nice to have that triangle. Now earlier I mentioned the identity for 2 sine of theta, or excuse me, sine of 2 theta. We're going to use that here. That turns into 2 sine of theta, cosine of theta, and the 2's are going to cancel. So one last peek at that. Let's go back up to, right there. 2 sine of x, cosine of x is the same thing as this down here, sine of 2x. Now when I substitute this in, this 2 is going to cancel with my 2 in the denominator. So that 2 and the 2 from this double angle formula are going to cancel. That's going to leave me with 625 over 2 times function 0 to sine inverse of 1/10 of theta minus sine of theta times cosine of theta. So let's do some substitution. It's not looking really pretty, but it does work out. 625 over 2. Plugging this in, it's just the sine inverse of 1/10 minus sine of the sine inverse of 1/10 times the cosine of the sine inverse of 1/10 minus 0. So our lower limit just gives us a 0. Now there is some simplification here. 625 over 2 arcsine of 1/10. This and this kind of cancel each other out. You've got a function and its inverse. They cancel each other out, gives you a 1/10. You can play around with this. If you were to draw the appropriate triangle, which would look like this, sine inverse of 1/10 means the sine of something equals 1/10. Sine is opposite over hypotenuse, so that gives you square root of 99 over here. And the cosine of that would then be square root of 99 over 10. So square root of 99 over 10 minus 0. So, and you can put it over 100. Okay, a bit more challenging on that one, but again, doable. A couple of the things that I'd like you to see on this one. Let's go back because this was such a long problem. Let's see. So at the start of this, we decided that, you know what, this just doesn't fit any of a lot of other things that are possible, like simple U substitution or rearrange the integral. It's not a partial fractions. Integration by parts, kind of saved for last. So we did try our trig substitution, seemed to make good progress with that. The only hitch came in right here is that because we had limits of integration, we had to change our limits of integration. And so what I did was I said, all right, well, x is 0, that gives me theta is 0. But if x is 1/2, well, then I had to actually solve and figure out what theta was. And I got theta by taking the inverse sine on both sides. So that gave me this really awkward limit. But you know what? It works. If you check it out numerically with your graphing calculator, it works. Now our substitution led to some cancellation. So we got rid of those, just had a sine squared. That's normally not a problem, but because we had limits of integration, and particularly these ugly ones, it was a little bit more work. We used the power reduction formula for the sine. Sine squared got replaced by this. The 2 comes out in front. Find the antiderivative. That brought us down to here. At this point, we realize, oh yeah, we need to draw ourselves a triangle. When you draw that triangle, make sure that you've got this term here, that square root term that corresponds to your integrand as part of that. This, of course, would be theta. We use our double angle formula when we found the antiderivative. We use a double angle formula to simplify this expression. That got rid of the 2 and replaced it with sine of theta, cosine of theta. The 2 canceled out. Sine of the sine inverse, those cancel out. That gave me the 1/10. Cosine of the sine inverse, well, I had to draw another little triangle for that one. Since theta was the sine inverse of 1/10, we had sine of theta is 1/10. These two are two sides of the same coin. And it's from this one that I drew this triangle. All right. With that triangle, you're actually able to calculate the cosine of this angle as adjacent over hypotenuse. So square root of 99 over 10, and voila, there's your answer. Okay. Wow, that was a good one. Let's do some more. All right. And I want to take on a problem that has a little trick into it that we haven't seen before, just to kind of make you aware of some of the things you can do. And let's write that one down right below all this mess. So this is our 5th problem, I think. No, 4th problem. 4th problem. Integral of the square root of 4 plus x over 4 minus x, all of dx. Okay. Oops. Zoom back here. What I want to do is I want to multiply by the number 1. And I'm going to multiply by the number 1 in a peculiar form. 4 plus x, 4 minus x. I'm going to multiply by 1 in the form of the conjugate. So 4 plus x, 4 plus x. So this is the square root of 1, essentially. And multiplying by 1 isn't going to hurt anything. Let's see what this does to everything, though. In the numerator, let's just work on these things separately. 4 plus x times 4 plus x, that's going to give me the square root of 4 plus x squared. And in the denominator, I'll have the square root of, well, you got to FOIL this out. So you're going to have this times this. And I hope that you can trust me when I say we'll end up with 16 minus x squared. Let's not forget our dx. All right. So 4 plus x over 6 square root of 16 minus x squared dx. Now some of this looks pretty close to something that we've done before, and some of it doesn't. So something that we've looked at before is right here, the inverse sine. If you have some constant term or just a dx over something like this, you can integrate that as the inverse sine. And that's close to what we got right here. 4 over this, that looks pretty good. But then you've got this x over the square root term. So kind of being torn in two directions. And the thing to do is to split up that term. So let's do that. We're going to split up this term into two parts. So let me rewrite this as the square root of, that's going to be 4 over the square root of 16 minus x squared dx plus the integral of x over the square root of 16 minus x squared dx. Yay. Well, that's good news. That's really good news. This first one is going to integrate as 4 times something. Well, I've got dx over square root of 16 minus x squared. That's exactly my inverse sine there. So it's going to be times the inverse sine of x over 4. Let's get back there. So x over square root of that is going to be 4. Plus this one, I'm hoping you see what we're going to do with this one. You've got a squared term here in the denominator and a linear term or first degree term here in the numerator. That's just begging for a U substitution. Now I'm not going to take the time to show all the details here, but if you let u equal 16 minus x squared, your du term is going to have a 1/2 part of it that's going to cancel. Some of our extra stuff here will end up with -1 over the square root of 16 minus x squared plus a constant. But the moral of the story is you can do the rest of this with a nice little U substitution, and you're done. Yay. All right. Pause the video, take a big stretch, get a glass of water or other beverage of your choice, and get ready for a couple fancy U substitutions. That's what's coming up next. So, fancy U substitutions. So this was just a regular old boring garden variety U substitution. U is this, du is minus 2x dx, and minus 1/2 du equals x dx, and on and on. All right, that's just a pretty generic, boring U substitution. We're going to do some U substitutions on steroids, some really fancy ones. So what do I mean by that? Well, let's start with this one, for example. So it's our fifth problem. Integral of 4 over 4 plus e to the x dx. Now again, how do you know what to do? Well, you know, it's a little bit of luck, it's a little bit of experience, practicing a lot of these things, watching some really well done videos, all that stuff adds together. Now, because I've got this transcendental function, this e to the x term here, it's not going to be something nice and cute with partial fractions. It's not any of our trig substitutions. You could try integration by parts, but before I get to integration by parts, let me show you another trick. Let's let u equal 4 plus e to the x. Okay. And let's calculate du equals e to the x dx. And I'm looking here and I need to solve for dx. So, okay, well, I could get dx by dividing by e to the x. That's my dx term. But this is a problem. I can't mix up my variables. I can't have u and x at the same time. So how do I get around that problem? Well, I can get around that problem this way. Let's move the 4 to the other side. I get u minus 4 equals e to the x. So I can take this and plug it in here and get du is u minus 4. Okay, that's what I needed. That's my dx term. Let's put a few things together here. If I'm going to make this u substitution, let's take the 4 out in front. And then I'll have 1 over u. Now let me write it like this. 4 plus e to the x dx. Maybe it's a little clearer to see here. This is 1 over u. That was my original substitution. 1 over u. And then dx is du over u minus 4. And those multiply. Now I'll keep that 4 out in front. Just write it like this. U times u minus 4 du. And it seems like it's gotten no better at all. It seems like it's a big mess. But there's actually stuff that we can do on this one. And that is, we can do partial fraction decomposition. Let's let 1 over u times u minus 1 equal, well, a over that term plus b over this term. If I multiply both sides by my lowest common denominator, which would be u times u minus 1, everything gets multiplied by u times u minus 1. So, let's try and squeeze it in here. U times u minus 1, u times u minus 1, u times u minus 1. So I'm not leaving anything to imagination. That cancels. That cancels. And that cancels. So what are we left with? We're left with 1 equals a times u minus 1 plus b times u and now we can solve for a and b. Let's see. To solve for b, I can set u equal to 1. Let's do that. If I set u equal 1, then what's that give me? It gives me 1 equals a times 1 minus 1 plus b times 1. Since this term disappears, I guess I'll end up solving for b here. That term becomes a 0. I end up with b equals 1. What else could I choose to set u equal to? Well, I could set u equal to 0. That would wipe out this b term, set u equal to 0 and get 1 equals a times 0 minus 1 plus b times 0. Once again, one of our terms drops out. I get negative a equals 1. So a equals negative 1. Almost done. We got our partial fraction decomposition. Let's rewrite the integral. We can integrate, substitute back, and then solve. So this is where we're at. It decomposed like this. I had a negative 1 over u plus 1 over u minus 1. So 4 times the integral of negative 1 over u plus 1 over u minus 1 du. Both of these integrate pretty easily. That's 4 times natural log of, let's see, negative will come out in front. Natural log of u plus natural log of u minus 1 plus your constant. And way back at the beginning of this, we could substitute in for u. U was e to the x plus 4. So it would be e to the x plus 4 plus e to the x plus 4 minus 1. Now I've switched the order. It was 4 plus e to the x, but e to the x plus 4 minus 1, and then plus our constant. I'm not sure if WebAssign would take that or if they're going to want you to write e to the x plus 3. I don't know. I'd take that, although honestly we should probably simplify it a little bit, but that looks pretty good there. If you get that far, I will give you 100% on that problem on an exam. Of course, you got to show your work, but this would look good. So that's kind of a surprising use of a U substitution. They're more flexible than you might have imagined back in section 5.5 in your Calc 1 course. We're going to do another one like that. So grab a seat. This one's equally as challenging as the last one. So maybe we'll review the last one a little bit. We kind of wanted to get rid of this term down in the denominator. So we did a U substitution. It didn't really go very far. So then we said, all right, well, if I wanted to follow this, then I could move this underneath here. That gives me d over e to the x equals dx. I did need a substitution for dx, so that was nice. But I can't have mixed variables. I can't have u and x in the integral at the same time. It's one or the other. So then we realized, oh, well, moving this to the other side gives me a substitution for e to the x. And that's what I put down here. So that dx term, that whole dx term, got replaced with du over u minus 4. And at that point, there's just a partial fraction decomposition, and then substitute back in for u. One more fancy U substitution, then we'll take kind of a break here. So another fancy U substitution problem coming up. Let's separate this. Hope you're hanging in there. These are tough. There's no doubt about it. So square root of 100 plus e to the x dx. And boy, this just looks like nothing. Looks like a big, big mess. So what are we going to do here? Well, a natural thing to do would be to let u equals 100 plus e to the x, and you're not going to get very far. So what if instead I did that? Okay, nice, but I'm going to struggle to get a dx term out of this unless I do some more work. So let's do some more work. Let's square both sides of this and get 100 plus e to the x. Okay. And now I can differentiate with respect to x. In fact, let's see. Do I want anything else while I'm here? We'll come back to it as we need it. If I differentiate, I'm going to leave myself a little space here. If I differentiate with respect to x, I've got to use the chain rule. So it's going to be 2 times u times du by dx equals the derivative of that, which would be e to the x. Now, usually I don't show this step. Usually I just multiply both sides by dx in my head and end up with 2 du equals e to the x dx. Okay, well, that's fine. But kind of like the last problem, look at what I got in the integral. All I've got is a dx term. So that means I need to solve for dx. So let's play the same game we did with the last one. I've got a solution for dx, but what's the problem with it? The problem with this is that I'm mixing u and x. I need to get this by itself. Can you see how I can get that by itself? If I move that 100 over to the other side, then I can get u squared minus 100 equals e to the x. Perfect. So let's plug that in. 2u du over u squared minus 100 is my dx. Now, it might seem like this is getting really crazy, intense, and insane, but it is going to work out. Let's see that it works out. So that whole term is my u. dx is getting replaced by this whole term. So it's going to be 2u du over u squared minus 100. And let's clean that up a little bit. U times u is u squared, so it's going to be 2u squared du over u squared minus 100. Now back at the start of this, may have been easy to gloss over, but I said if you have a rational function, then we can use partial fractions. But there's one thing I did point out, that you want to make sure that the numerator degree is lower than the denominator degree. So let's see if we can't do that. We've got to do a little bit of long division here. We're going to take u squared minus 100 into 2u squared. Well, how many times is this going to this? Not very much, just twice. The one thing you got to be careful of is that 2 times this gives me 2u squared minus 200. And that we got to subtract. Now, can you subtract? Can you subtract for me? These are going to cancel. Well, what am I going to write down here? Is it a positive 200 or is it a negative 200? Well, if you change the signs and add, make that a plus, minus, plus, you realize that it's a positive 200. Now keep in mind, this is the remainder. So this expression up here can be replaced by, let's see, how do I want to squeeze it in? Can be replaced by this one down here. Integral of 2 plus 200 over u squared minus 100. Because that's what we just showed. Okay, this part we can integrate. This part, I'm afraid, is another fraction decomposition problem. If you set up and solve here, what you'll end up with is 1/20th for A and 1/20th for B. They'll be opposites in signs. What you'll end up with is something that looks like this. 2u. Do you really want to see it? Okay, fine. All right, we'll do it. For those of you without any patience, you can fast forward a little bit, but some of you might need to see that set up, so let's do it. So let's see, I'm gonna have, well, you know what, we'll take the 2 out. We'll just work with 1/100, or u squared minus 100. So I'm not going to worry about the 200 in the numerator because that's going to be a constant. So I'm going to take a look at 1/u squared minus 100 equals a over u minus 10 plus b over u plus 10. Like that. And like before, we'll multiply both sides by the lowest common denominator. U squared minus 100, which is u minus 10 times u plus 10. We're going to get some cancellation. On the left-hand side, that's going to cancel out. On the right-hand side, u minus 10 will cancel, leaving me with a times u plus 10 plus b times u minus 10. And the trick before will work here. We're going to choose some clever values for u. For instance, if I set u equal to 10, so 10 here, I'll end up with 1 equals a times 10 plus 10 plus b times 10 minus 10. And the nice thing is that this term cancels out. So I'm left with 1 equals 20a. So a equals 1/20th. You can play the same game here by letting u equal -10 and find b equals -1/20th. All right. Let's put that into our integral. This is going to become the integral. So, well, let me rewrite it. 2 plus 200 over u squared minus 100 du. Integral of 2 du plus 200 times the integral of 1 over u squared minus 100. Du plus 200 times the integral of a, which was 1/20th. So 1 over 20 times u minus 10 plus -1 over 20 times u plus 10 du. The 20s can cancel, can come out here, factor out and cancel out the 200. So that's going to be 2u plus 10. Now when they do, you can just integrate that pretty much directly. So it's going to be ln of the absolute value of u minus 10 minus ln of the absolute value of u plus 10 plus a constant. These can come together. So 2u plus 10 times ln of u minus 10 over u plus 10 plus a constant. You don't need to rewrite it like this. You do need to go back and plug in for u. So overall, it's going to be 2 times square root of 100 plus e to the x plus 10 times the ln of square root of 100 plus e to the x minus 10 over the square root of 100 plus e to the x plus 10. Whew. Good one. Good one. All right. I think after that, you need to deserve a little bit of a mind break. So let me continue my series of cool things you can do with your TI-84 graphing calculator that you never knew. And for this first one, I think we'll start with polynomial. In fact, let's take a look here at this polynomial. No, not that one. Over here. So x cubed minus 12x squared plus 47x minus 60. A lot of times what you're going to want to know is, where does this cross the x-axis? What are the roots of this polynomial? Now, if you got a nice program like Desmos, then you can figure that out pretty easily. 3, 4, and 5. But what if you're in a pinch and you don't have time to fuss around with your graphing calculator like that or with Desmos like this? If you're in a pinch, then go to the apps button and you can watch my keystrokes as I move along here. We're going to go to the apps button and then polynomial simultaneous equation solver. So we'll just type 9. And hey, first one, polynomial root finder. Cool, let's go there. Adjust the order of your polynomial. We had a cubic polynomial, so that one's all set. The rest of these, you don't need to mess with. So just hit the next button. To do that, we're going to hit the graph key. And you'll see I've already typed this in. So you can either type in the plus here. You can change it to a minus, or you can just type in plus -12. But just type that in and hit the solve key. So when we hit the solve key, bam, there you go. 3, 4, and 5. Just what we expected. So kind of nice. Now, a lot of times you might end up with decimal values, depending on if your polynomial has square roots, but at the very least, it gives you another way to quickly solve some of these kinds of problems if you're in a pinch. Okay. About 4 more here. So hang tough with me. Okay, so let's start out with a little bit of a harder one. I know you think all these are hard, so maybe I was being redundant in that. My bad. Integral of 5 sine of 2x over 1 plus cosine to the 4th of x dx And let's put that in view. Well, there's a couple things I notice about this one. The first one is that the numerator, we've seen that term before a couple times, I think. Sine of 2x is 2 sine of x cosine of x. And the denominator, boy, you know, those denominators, especially stuff like that, I wish I had something of the form here. An a squared plus a u squared, because I know how to integrate that. That's an inverse tangent. So, okay. Well, I can make this a squared. That's not so bad. So it's going to be 1 plus cosine squared of x squared. And if I made that a u, well, let's take a look up here. Now up here, I can replace this with 2 sine of x cosine of x. I still have my dx here. But let's take a look at what happens if I make u equal cosine of x squared. Actually, you know, most people write it like this to start with, but let me write it like this, cosine of x squared. I do this for my Calc 1 students especially because when you differentiate this, you've got to use the chain rule, which means the derivative of the outside, so du, derivative of the outside is going to be 2 times cosine of x times the derivative of the inside. And the derivative of the inside gives me a minus sine of x. And I've got my dx term here. That minus can come out in front. And let's just switch these around. Sine of x, cosine of x, dx. That looks really close to what I have here. The only difference is I got to get rid of that negative sign. So let's do that. So it's going to be negative du equals 2 sine of x cosine of x dx. Nice. So I'm pretty much ready for a U substitution. Let's see. That's going to become 5 times negative du of 1 plus u squared. And the negative and the 5 can come out in front. So negative 5 times the integral of 1 over 1 plus u squared du. And that's looking an awful lot like my arctan. In fact, as a bonus, since a is 1 for us, I don't have to worry about that term out in front here. That 1 over 1 is going to disappear. So it's just going to be the arctan of u over 1, or the arctan of u. Perfect. So negative 5 times the inverse tangent of u plus a constant, which is negative 5 times the inverse tangent of cosine squared of x plus c. Perfect, just perfect. And that's it. Yeah, I apologize for giving you one that's not 15 minutes long. I'll make it up on the next one. Just kidding, just kidding. All right, so spoiler alert, we're not actually going to do this one out, but just kind of a reminder. X minus 1, x squared minus 3x minus 10 dx. If you see something like this, rational function, especially if the denominator factor is pretty easy, then you might start thinking, you know, partial fractions. And I hope that you're pretty good at that one. So that's actually problem number 8 for us. Let's try another one. And again, this is not one that I'm going to completely do. I'm saving up all our energy for the last one. And we're getting close to the last one. I think I promised 10 problems. We're going to do that. So let's take a look at 3 over the square root of x plus 3 plus square root of x dx. Now again, all of our usual tricks don't seem to really want to work out. But there is one that I haven't shown you yet, probably a lot that I haven't shown you yet, but one in particular that might help out for a problem like this. 3 over the square root of x plus 3 plus the square root of x. What if I multiplied by the conjugate of the denominator? Now the reason for doing that is when you multiply a plus b times its conjugate. Now its conjugate is just going to be changing the sign on this, a minus b. Then, well, what you get is a squared minus ab plus ab minus b squared. And these middle terms will cancel each other out. Just left with a squared minus b squared. Okay, great. Why does that help? Because if I could square these and get rid of them, then I'll be left with a subtraction and the x doesn't cancel out. Things might work out pretty good. So let's try that. The conjugate for us here, I have to multiply by that in both the numerator and denominator, would be square root of x plus 3 minus square root of x. And we got a dx term hanging out here. Now a lot's going to happen here. This is going to fit the pattern that I had down here. And to kind of save ourselves a little brain power, square root of x plus 3 minus square root of x. There we go. In the denominator, let's just jump to the happy ending. It's going to be a squared. What do I get when I square that? X plus 3. What do I get when I square b? B is the square root of x. Just x. And if you notice, x minus x cancels. And in fact, the 3 here in the denominator will then be free to cancel with this thing up here. So what you're left with is the square root of x plus 3 minus the square root of x dx. And I apologize, I was a little bit light on the details here. Like I said, these terms cancel. So all I'm left with is a 3 in the denominator. And since that 3 can cancel with this, because they're multiplying the whole term here, when I cancel that, all I'm left with is this. That you can finish integrating. All right, plenty of bonus points here for you if you're still with me. Make sure you write in your notes, Euler. One of my favorite mathematicians, Leonard Euler. So we'll talk about him later in the course when we look at something like this. E to the I pi equals -1. Or better yet, if I move this to the other side, e to the I pi plus 1 equals 0. An absolutely beautiful formula. It involves, in a very simple, elegant formula or equation, the 5 most important constants in math. E, I, pi, 1, and 0. We will prove that before this semester is out in a way that you can understand. For now, let's finish up with our 10th one. Okay. All right, so like you, I'm getting a little tired, but this is our last one, so let's get it done. When I look at this, you know, I start thinking, well, maybe a U substitution. And let's see how close we get with the U substitution. If I let U equal the denominator, and that makes sense because I got a squared term here and I got a first power term here, you differentiate, you're going to lose a power. So x squared minus 18x plus 82. I'm going to differentiate, U equals 2x minus 18 dx. And I'll notice that I can factor out a 2 here. Then I got an x minus 9 term, but here I've got an x minus 7. So I'm close, I'm not quite there. So here's what I'll do. I'm going to subtract 2 from that numerator term. I can't just subtract 2 and not adjust for it in some way. So the way I'll adjust for it is over a similar thing here by adding 2. All right, so at least this first one can get out of the way pretty quickly. This is now x minus 9, x squared minus 18x plus 82 dx. And now I can finish my U substitution. I get 1/2 du equals x minus 9 dx. So that's perfect. This right here is 1/2 du, and that's my u. So let's finish this up. 1/2 du over u is 1/2 ln of u plus whatever we get over here. This one's going to be a little bit more work. What does catch my attention on this one is that this is close to a perfect square. Remember what a perfect square is. Perfect square would be something like this. Let me write it down here at the bottom. A plus b squared is a squared plus 2ab plus b squared. Or in our case, a squared minus, or a minus b squared is a squared minus 2ab plus b squared. So it almost fits that pattern. It almost fits x minus 9 squared. What caught my eye was the 82. 82 is just one more than 81. If this was an 81, I'd be in good shape. In fact, let's make that an 81, sort of. 2 over x squared minus 18x plus 81 plus 1. Okay. Why did I do that? That's because this becomes x minus 9 squared. And I can think of that as 1 squared. Does that help me out at all? Absolutely. That 2 can come out in front. But this, for the last time this evening, is our inverse tangent. We've set it up as our inverse tangent. So to finish this one off, that 2 is going to come out in front. So we'll end up with 2 times 1 over a, which is 1. Didn't show that last time, I will this time. Tangent inverse of this over this, x minus 9 over 1 Let's not forget our constant. We've got to go back and substitute in for u. 1/2 natural log of, that was x squared minus 18x plus 82 plus this. I'll clean that up a little bit just for good looks. 1/2 ln of x squared minus 18x plus 82 plus 2 times the inverse tangent of x minus 9 plus a constant. Mercifully, that's it. Good luck with this stuff. This lecture goes really wonderfully with my WebAssign homework on this. So if you've taken good notes, it should really help you out with the stuff. Catch us in office hours with some more questions. There's help on WebAssign. There's a lot of watch it. There's, I think, a possibility to chat with a technician. Not a technician, but a tutor through WebAssign. It's not my office hours or my SI's office hours. So please get some help on this. I know it's tough. I'll help you with it. We'll get through it. All right. Have a good one.